Okay, you can. Okay, can you hear?
Can you say it on?
Yeah, can you hear me?
Yes, I can.
Yeah. Okay.
And then
Video.
yeah, sure. And then share the fourth one, maybe Carl.
Oh yeah. Let me get rid of this.
Yeah. Maybe don't wait the kids. Oh, there we go. I think we're doing yeah, very nice. Collaborator, yeah, and then we got full on the total of those. The last week, at the to allow me to use personalized for my bill today. Because I don't need slides and so I think it's useful to show some graphs. On the whiteboard, you can also, graphs. Let's start. Okay, we will generate until then some stuff. Yeah. Oh yeah. I started first in the concept of one model. Usually the time we find that one model, or many models. So if the difference is the combination, small bar. Thank you very much. we start?
Yeah, okay. Okay, hello everyone. Today we're very happy to have Kaoru Hagiwara to visit us and give us this talk. Kaoru has been working on many aspects of particle physics and phenomenology. We have a very broad and deep knowledge in many aspects. So if you have any questions, please ask Kaoru and make use of this stay here. You'll be here. We're leaving tomorrow. Right?
Tomorrow.
So we can talk and ask any questions if you want to visit and let me know if you want to join dinner. Okay. So Kaoru will be giving us today in particular for today's talk, we will talk about CP violating top-Higgs coupling in SMEFT. Kaoru, please.
Yes.
These are points.
I see. Okay. So today I will talk about the subject of possible CP violation in the top-Higgs sector. It is the kind of heaviest sector of the standard model. So the alone gives us some motivation, but if there is a source of the CP violation there, it is associated with a big coupling, so it might have some impact from including possible value differences in the electric test. So there have been and I worked on this subject. So I started on 2017 and I looked for my researchers and I first studied E plus and minus invariance, and actually each one had something in it because I don't like to write a paper without having anything in it. So every time I had something in it. And in this case, this is a linear polarizer project. So it's I studied this process of 500 TeV and 1000 TeV. But and because this is E plus and minus linear polarizer, I thought that I should at least try to see the maximal information we can get. So actually, in this paper, what we did is that each T decays into three bodies, and in total we have 7 body final states. We studied 7 body final states complete distributions with correlations and try to obtain the maximum information about CP violation. This kind of experiment should be possible in class polarities. And when we did it, what I did was usually these all the information is in this E plus and minus divided 3P and 3P. So essentially, P and P has 2 heavy states, so there are 4 heavy state combinations. Maybe for initial state, left and right, so there are 2. And so all the information is in the heavy amplitudes, so essentially 4 heavy amplitudes. But because of interference, we have 4 times 4, 16 elements in the so including all the possible correlations between P and P. And in order to make use of it, what I did was we introduced the top decay density matrix, which had a complete 3-body distribution. So top 3-body decay into D L plus U or D to D D bar U. D bar U is from W, but including those the complete decay, I obtain the density matrix. Okay. So it's a kind of yeah, but top is has only sigma half, so it's very simple 2 by 2 matrix, but it's in the 2 3-body things. So this is explained in this paper. It's quite useful when we want to study the polarization information from top decay, because decay density matrix can be used for any place, right? So LSC experiments can also make use of it. one thing which was very important about this dependence matrix is most important polarization information about the top is obtained in case of the semi-reference, because everybody knows that it is obtained by the charged electron distribution. Okay? And like that, exactly the same reason, when top decays completely harmonically, the information is given by down type Z. Okay? And in this study, what I did was essentially when W plus decay into up pole and anti-down pole, I assume that it's completely impossible to distinguish between up pole and anti-down pole. Okay, and then obtain all the results. In principle, up pole and anti-down pole can be distinguished by using just that technique recently. Improvement is very significant, but I think it's the hardest because it's only 2/3 versus 1/3. So the difference is very, very small. So I guess it's very hard, but still that may improve a little bit. And also, let me see, charm and strength. This distinction can be done. Maybe at least 20% or so, and this will improve it. In this particular analysis, I took all those future probability as a parameter which can improve our dependence matrix, but I just said that it's a 50-50. But it is very important we should make use of the WDK information. That's the only quantity which really tells about the polarization when optical decay harmonically. So this is the optical study, and in this case, single top plus Higgs is essentially weak process. Using virtual W collide with the equal, and it produces top-Higgs. This is single top reduction, and then this top-Higgs need to fix this. Okay, but the important thing is that exactly the same process, Higgs boson can be emitted from the W channel. Okay? And because of this, interference between WWH coupling and PTH coupling, relative phase can be made. And that's the important thing about this data. Okay. And I was interested in this process because it has been well known that when we change the sign of the Yukawa coupling, just from the standard model to just a negative coupling, then the cross-section jumps by a factor of 10. So it means that there is a very strong destructive interference between the diagram with the WWH coupling and PTH coupling in the standard model. And so maybe it is interference makes the cross-section 1/3. And by changing the sign of the PTH coupling, this now becomes a constructive interference. And this ratio, 3 versus 1/3, is kind of 10. Right? So this kind of interference was there. I already knew. And if there is such interference, the sensitivity to CP phase should be very big. So the signs are kind of CP phase type of the coupling.
If we change the sign of the PTH coupling, we will modify its gamma. Because the Higgs to gamma is the negative interference of W lead and the top lead. And if you completely change the top Higgs sign of the Yukawa coupling, we will increase the Higgs to gamma.
I think so. Maybe it's really how it's, yeah, that's kind of I remember that family that kind of happened. But actually, my interest was a very tiny phase. So this is this fact has been known, and it motivated my work because there is a big negative interference, and this negative interference is physical, and it helps measuring the even small phase.
So if you introduce a phase, you just have a new kind of is it going to interfere at the top the amplitude level,
Yes,
or
of course.
okay.
Yes, that's the only way to measure CP violation. So actually, in this paper, what we did something new is essentially to study the top polarization in the scattering plane. Let me see. So for instance, we have W is coming in, and D is coming in, and then P is coming out, and 6 is coming out. So you can think of this kind of scattering, and this comes from, say, U. Okay. And we studied all the correlations, including this correlation. But the most important thing we found is that in this scattering plane, the top of polarization perpendicular to this scattering plane, whether it has a polarization towards this direction or towards that direction, is sensitivity to the phase. And the sign of the phase is determined by measuring this polarization if CP violation exists. Okay. So something like that. This is what I did here. And in this paper, they are by the same because actually all the work is done with Yahian Zen to note these slides. Okay. And in this paper, we just extended this study very carefully, and what we study is this distinction between CP asymmetry and the so-called naive P asymmetry, and we also define naive CP naive P asymmetries. And here, what we, especially here, what we did is we artificially make the top decay uses 10 times larger so that we can see the effect very clearly. And then this type of asymmetry can appear from the final state phase, and the simplest way to show that such asymmetry appears is just by studying CP asymmetry. Okay. All those things are explained carefully in this paper. So if you are interested in those symmetry property of the asymmetries, please read it. And so this is the explanation of our past works. And today I am going to talk about muon collider works, and please let me start with these slides. So please let me skip those. Okay. Actually, I was not interested in this subject until Yahian showed me this figure. This is the total cross section from mu minus mu plus to mu bar, pp bar h. And this is the phase of the Yukawa coupling. Oh, maybe I didn't define the Yukawa coupling. Maybe let me go back. Yes. Here is the phase, and G is real positive, and we just introduced the phase here. And if C is pi, the coupling sign changes. Okay. So between the 0 to pi, we have the range, and because we want to, when we study CP violation, CP autosymmetries, we want to compare exactly the magnitude of the phase and the sign of the phase. Determination is essentially CP violation test. So we choose the range of phase between minus pi and pi. Okay. So
But
this is.
there is an indirect, for instance,
Hmm?
right? There is an indirect.
Oh yes, yes. There are many. Yes, yes, yes. Yes.
Just to be sure, so
Mm.
yeah, I guess in the master of the top doesn't have any or something because in case when you can perform pilot transformation.
Yeah. Maybe after we give this in SMEFT, you can see the relationship. Yeah, once you have Lagrangian, it's obvious. Huh? HTT coupling. Yes, this is the phenomenological coupling which we use all in the 1, 2, 3 paper. Okay. Okay, so this is the starting point of our study, and well, because it's the cross section, it depends only on the magnitude of phase. Okay, and between 0 and pi, I told you that in case of a single top plus H, there is a factor of 10 difference, and that's okay. And in this case, at around 1 PV, the difference is about factor of 3. It can be explained as a consequence of the interference. But what was shocking was that when we increase the energy of muon collider from say 1 PV, 3 PV until 100 PV, I asked her to make it because what she showed me was 30 PV in the beginning. And oh, this is crazy. So from here to here, I don't know how many orders, 1, 2, 3, so more than 1,000 difference. this kind of interference. So, so that's why I was interested in this subject. Okay, of course I first looked at the program had some error, and then the next thing I asked her is to please show the square root of S dependence. So these are discrete, but I really wanted to see the energy dependence of the cross section for given phase, and then I could immediately see the hint because at high energy, all those non-zero C cases have linear behavior in log plot, and we can clearly see that this is the square root of S to the square, so it's proportional to S. Okay. Now, if it is proportional to S, I'm kind of an expert in studying weak boson scattering in very early days, and this is a breakdown of these environments, right? Because this what is different for this process compared to all the others is that this process contains weak boson field. Okay, so this kind of diagram, okay? And if this amplitude is not gauge invariant, of course, the weak boson polarization vector grows with energy over mass. Okay, and there are 2 of them. So actually, this is completely explained by this kind of energy over mass. So because I was sure about this, we decided that let's study WW, also WW to pi-pi+ttH. That's what we do. Okay. And this is the result. So as we expected, WW to pi-pi+, and we just study W because I know that the transfer study doesn't do anything. Okay. So we just calculated. In this case, WW invariant must be really started from the kind of near threshold to 100 PV, and then it's very clearly period.
But really saying that you get to the scale of the dimensions.
Of course, and it's hard beyond. I will go back to the unitarity limit of this this scenario at the very end. So this is the Lagrangian technique. So I realized that this should be related to the gauge invariance of our effective CP violating top-Higgs. So I try to think. Of course, I can start from kind of 2-Higgs doublet or something. It is completely gauge invariant, flavor diagonal, and still can have a CP violating top-Higgs. But then I thought that maybe in order to avoid sensitivity to that particular UV model, I thought that SMEFT may be a good intermediate step which we can try because it's simple. Okay. So we looked for the operator, and luckily there is only one operator in SMEFT dimension 6, and that's this operator. Very, very simple. It's essentially this standard model, Yukawa, and this times are just so obviously the environment. But now this phase should be absorbed. Yeah? But we know that this phase can survive. Okay? Because there's no new particle to absorb the phase. Okay? So this is essentially the Lagrangian detail we use, and then we just make expansions of, because at data stage we use boson integral theorem to check the results, and so we have complete Lagrangian. But because this is so simple, this is complete Lagrangian. Very, very simple. I didn't make a standard combination of terms which allows us to read off the primary easily, because this is so simple. I felt that I want to see the gauge invariant structure of the interactions by just watching this one. So it is slightly complicated, but it's very simple. But after this renormalization of three-level renormalization of the operator distributions, we have the standard top master, and this is the standard model of this. After this absorption of the Excel phase, we have just the standard model gone. Okay. So the standard model H. Okay. And then what is important is from this higher dimension operator, we have more terms, and we have one term which has exactly the same form as the standard model coupling. And by just choosing this coefficient as a difference between our complex Yukawa and the standard model Yukawa, then after you just by summing this term and this term, standard model Yukawa is just replaced by complex Yukawa. This is the trick with that. It's obvious. Once you do it, the Yukawa coupling just becomes all arbitrary. Both G and C are completely arbitrary. Okay? And then with this same coefficient, so this is the term essentially this number. Okay? So the Wilson coefficient of the dimension 6 operator, we just make it a complex number. And then exactly the same number, we have higher dimensional terms. And we will see that these terms are very important. And when we study WWPTH, actually, we find that there is only one diagram in addition to the PTH coupling, which is introduced by this gauge invariant description of the complex phase, complex Yukawa. That is T, okay? And also here, HHTT. Okay? So So there are two places where this HHTP contact can be automatically. And now that's the only one. So if we choose the unitary gauge, all the others can disappear. And there's one more thing like HHTP that it doesn't contribute to the result. Yeah. So this is the only additional diagram we need to keep. And this is so easy. So, all the, actually in this case, in math graph, there are 20 diagrams. Okay? And so, of course, I didn't want to calculate 20 diagrams by hand, but this I can do by hand. Okay? So the point is up to 20 diagrams, I allow the numerical program to calculate amplitudes. And this amplitude, actually, I made two versions. One I calculated by hand, the other we made a numerical program just to calculate this and just average. Okay? And that's how we start. Now, after adding this, what happens is, can I use this? Maybe. Oh, no, it doesn't go. It's okay. It's very easy. Yes, no problem. So after adding this, so this SMEFT is after adding this one, we got this, and actually it doesn't look so much different. So actually, in the beginning, I didn't understand this because all my past knowledge about boson scattering is if we make the interactions completely gauge invariant, all those high energy going amplitudes disappear and become very mild, right? But in this case, actually, the magnitude of the total cross-section reduced by a factor of 1/4. Yeah. But this S behavior survived. And very strictly, once I understood the reason, it was very clear. But very strictly, I first thought that, oh no, probably, we did some kind of patchwork, right? I mean, the main part with the complex Yukawa was calculated by MATLAB, and we made some new things and I first thought that, maybe I made a mistake in the relative sign of this new vertex and the MATLAB, which is sign that. So we tried many things, and so for a moment, I maybe almost 2 months, I thought that maybe I made a mistake. But then I realized, if this is correct, I should be able to check the correctness just by using Goldstone theorem. And Goldstone amplitude is so easy, I can calculate it by hand, right? So that's what I did. So actually, this is the correct result. Okay? And they can see this is a square root-based dependence of the SMEFT. And just for comparison, we compare complex Yukawa and SMEFT times 4. So this is a strange thought that actually this fact remains as our last mystery. Okay? So the whole point is, my first story was, this growing cross-section is just an error. There is no gauge invariance, and because of this, equivalence theorem is broken. And then by making the theory gauge invariant, we should be free from this. Okay? But at the very end, what we found is that this correct cross-section in SMEFT is just 1/4 of the complex Yukawa. This was very strange, really. So until we found the reason why this is happening, at least in the explainable way, we couldn't write this up. So that we can, I can give or receive the talk. It means that we understood at least why, in which way this is happening. Okay. So the point is, when we do Goldstone theorem theory, we should go back to the Lagrangian. Actually, this is a common, very common warning for everybody who are doing SMEFT. So it's very clear that if we do Goldstone equivalent theorem calculation, it is just a Goldstone. My Goldstone bosons are pi's, okay? Pi 0 is a Z boson boson, and the pi minus is a W minus boson boson, and there is an emission quantity to everything. Okay? So the point is, in this Lagrangian, if there is no, there are terms which is dimension 6, because this is dimension 6 operator. If there is no vacuum expectation value among here, then actually the field operator gives dimension 6. Okay. That's very important. And you can easily see, here is pi plus pi minus, here is the h, and the t, and theta. Okay? So it means that all dimension 6 is given by the field, then it means that amplitude behaves as dimension 6. And this leads to linearly rising process. It's unavoidable. Okay? So whenever you use, dimension 6 operators, all of them happens. When you do Goldstone boson, so actually, when the final, so if you use bosonic dimension 6 operator, 2 bosons to 4 bosons amplitude actually gives the leading contribution of time, and you shouldn't forget it.
So in other words, if you resolve these operator via the second Higgs, this or high dimensional operator could be generated by the integrated algorithm of the Higgs. And once you cross the threshold of the second Higgs, you will see the cross sections.
Yes, that's related to unitarity bound. So I will come back to that. Yeah.
Well, what is the scale lambda that you in the population?
Yeah, it's very big. Now that's very small. It's essentially big. Yeah, because for instance, if we make the magnitude, if we make the magnitude of the Yukawa coupling the same and just change the sign, okay, then the coefficient is here. So it's twice the standard model Yukawa coupling, right? So the change from the standard model Yukawa is twice the standard model Yukawa, which is the biggest coupling in the standard model. That's a huge reveal. And if we write it in terms of lambda, that if we set lambda to be 1 TeV, for example, then this small, the Wilson coefficient is, I don't remember, but maybe 20 or 30. Huge number. Kind of full party. Yeah.
How the one can see if it's the example.
Yeah.
That means the small coefficient, small lambda or not, that's squared of the one will be squared. So,
So the important lesson is that when you think that you are changing the phase or sign of the Yukawa coupling, you don't feel like you are introducing huge coupling, right? But actually it's wrong. Yeah. You are making a very huge contribution. And because of it, if you do it, actually the unitarity bound is very low. I come back to it. Yeah, it was fun because I didn't expect this. So each time we found a solution, I really enjoyed. Okay. And so this is the Goldstone boson equivalent theorem. Okay. This amplitude is leading contribution. It's obvious, okay? Because all the others are separated by 1 power of s. And anybody can calculate this instantly. Okay? And this amplitude is here d, so it's this is the exact amplitude. It's so simple. Okay. Oh, actually, let me see. In order for this amplitude to behave, exact amplitude behaves very simple. We need to choose the pp bar rest frame when we define the helicity of T and T bar. Those are technical things, but in the rest frame of pp bar, if we choose the same helicity for T and T bar, we can obtain the full matrix element when pp bar is in spin 0. Okay? That pp bar is spin 0 is obvious from the VCR angle. And so this is just technical thing, but once you know how to calculate the helicity, it's kind of this is something. Important thing is that helicity depends on the plane. So you need to always choose the right plane in order to obtain the very simple, elegant form that you can.
I have a naive question. If I go back and try to, not this slide, but try to leave pi minus pi plus from 4, does it cost me power coupling?
No, that's completely wrong.
Yeah, I know, but I just forgot to define.
Yeah. The easiest way to extend is to write down the full amplitude in Feynman diagram gauge to time to use. But the standard approach is that if you do the calculation in unitary gauge, the right turning couples to weak boson. Okay? And this weak boson can be decomposed into helicity +1, -1, and 0. And this helicity 0 weak boson that's coupled to lepton pair. And when we use this longitudinally polarized weak boson for the half scattering piece, we can replace the longitudinal polarized weak boson by boson. In my gauge, Feynman diagram gauge, which I recently introduced, the W propagator has 5 times 5 components. 4 components are kind of vector boson-like, and the 5th component is like a Goldstone boson. Okay? And then this 5 times 5 propagator contains a transition from the vector boson piece to the Goldstone boson. It is this transition piece which is contributing. Yeah. There are many ways. So in any case, and then what was very interesting is that this is Goldstone boson amplitude. So actually, this behavior at high energy behavior is explained by this diagram, which is here. Okay. And then I thought, I wonder what this, complex Yukawa is giving. Okay. And although I couldn't tell, in case of this, we have 20 diagrams. Yeah. So, but I knew that adding this diagram in unitary gauge to 20 diagram in unitary gauge, we get this one, right? And this diagram is easy to calculate in the unitary gauge because it's clear, right? It's very easy. And important thing is this initial W polarization vector is E over MW, okay? But this E square is kind of cancelled by this S channel Higgs propagator, right? And because of this, the total power of the amplitude is this and this is the same. And actually, because the structure of a fermion scalar point is exactly the same, actually their helicity amplitude is really almost the same. And if we make a high energy limit, actually we can tell that this unitary gauge amplitude is exactly 3 times this Goldstone boson amplitude. This is just a calculation. I don't know why, okay? But this is what the calculation tells. Now this explains the reason for 1/4, because 20 diagram times plus this 3 times this is this Goldstone boson theorem tells this figure B that this one is 3 times this figure B. So this sum of all the 20 is just minus 2 times figure B. And the figure B is the Goldstone boson amplitude for the correct SMEFT. Okay? So figure B gives the asymptotic cross section for SMEFT prediction. Okay? And that the first 20 diagrams is complex Yukawa diagram sum. Okay? And it is twice the asymptotic amplitude of the SMEFT. So absolute value square is just a 4. So this is, we understand, at least this is the reason why the sum of 20 diagrams is complex Yukawa. This cross section is exactly 4 times bigger at high energy. I don't know why, but this is what happens. Okay.
I think the 3 the 3 may come from the dimension 6 operation in the expansion. It was here for the TTH compared to the TTH to 3. So they might have to call it.
Yeah, so of course, I don't have the answer, okay? But what this means is that if there is a kind of a non-SMEFT type effective theory, okay, maybe non-perturbative, okay, which does not have this coupling, okay, that its Goldstone boson limit is just this. Okay. If you can find such theory, yeah, that's very interesting. Okay. But in my memory, what I wrote in our paper, which will appear very soon, I said that until such realization of gauge invariant complex Yukawa model is found, we propose that we use this SMEFT as a kind of representative of realization, gauge invariant realization of the complex Yukawa. That's our approach.
You're saying technicolor, you have to wait immediately biased.
I think
Technicolor. You said that you wanted to have a strongly coupled version of the discord. That would be a strongly coupled version. There would be no
it's very difficult because we have spoken in the external one.
Yeah, that's it.
So it doesn't work so easily. Yeah, but what you said might be one way of thinking. So whether we can make the Higgs sector non-perturbative while having a kind of a light resonance in the 125 dB and still make things okay, because
but then it's composite Higgs.
yeah, but the point is this composite Higgs should not appear here. So I really do not know.
it's increasing relation in a sense. If I do this complex topic power calculation, none of those two diagrams will exist. It only exists there are three others than one diagram.
Yeah, so this may be a mystery for me, and it's for you also.
Yeah.
So please think.
Okay, so the other three diagram that happen to equal.
Yeah, it's very interesting, isn't it? Yeah, just exactly -2 times the SMEFT, Goldstone boson amplitude. It's very, very strange. Yeah. So it suggests that can be something, but at least I couldn't find anything, and we shouldn't wait submitting a paper. So we decided that we just go ahead.
And this is just once we solve this problem, even the new this, we can do the calculation in SMEFT. Then the result is far more mild, but still there is a hint of those rising. Yeah. Now, because of this rising cross section, everybody worries about the unitarity bound, but now we realize that the 2 to 3 can be even more important than 2 to 2. And when I study literature on unitarity bound, everybody just doing 2 to 2. So I thought that, how should I do? And then, of course, we should use optical theorem. So this is what we do. So this is our optical theorem. Everybody knows. So imaginary part of towards scattering amplitude is just kind of starting from the same initial state to every final state which have the same quantum number as I, okay, in the theory with sum up. Okay. This is a standard of the theorem. It's just essentially the same as in theorem. Okay. And this condition, important thing is initial state should be j equal 0, spin 0, and also this whole amplitude should be spin 0. And actually, it is not at all easy, even for me, to project out the j equal 0 component of the amplitude when we have 2 to 3 amplitude with the internal extent. That's very hard. If it is only 1, 2 to 2, then anybody can do it. That's why you example from me and everything. But 2 to 3, I need to combine amplitude and your momentum, and then add angular momentum. So it's very, very difficult. What we found, nevertheless, is that this. Sorry, I did only this WW. Whenever this Goldstone boson amplitude gives a very good description of the total amplitude, it means that it is j equals 0 dominant, because this Goldstone boson amplitude comes from this diagram. It's completely j equals 0. Okay? In any channel, okay? But we just study pi plus pi minus here, but it's j equals 0. Okay? So actually, I thought that we just calculate all the cross section and sum them up, and then just study the region where the unitarity bound is such a hit, and if the cross section is approximated by the Goldstone boson amplitude, then it's okay, because the Goldstone amplitude is completely zero. Okay. And that's how we justify our unitarity bound.
The Goldstone amplitude is equal 0 is only for this set of diagrams. For other processes, they may not be.
Yeah, but it's clear that that's problem. If you propagate that, it's done by it. There is no for this process. Yeah, for this is contact interaction. J equals 0, and it dominates the time. So the only question is whether the boundary is reached if this diagram dominates, this we can just check. That's okay.
This diagram will be cancelled by three.
What?
It will be cancelled by three.
Do you mean using computation?
Yeah.
Yeah, of course. Of course. So that's why. Yeah. So this is very difficult. Okay. So the rule of the game is that we just try to take the effective theory until some limit. Okay. And then at least no way to go beyond is given by unitarity bound. And usually, or almost always, new physics appears far before the unitarity bound as is. This is understood. But it's just kind of rule of the game. When we set unitarity bound, we just assume that this theory continues and then it fits the unitarity bound, and
Especially because you're assuming that it's going to be equations. So the new physics is actually way over.
I think so. Yeah, but
That's if you had a strongly coupled.
yes. So this is the final result. Okay. So this is what we did for WW to TT and TTH. And actually, just by studying the Lagrangian, we know how many properties there exist with this high energy behavior, the same high energy behavior from just by watching the Lagrangian. And we sum them up, okay. And then maybe everybody knows that with this effective operator, WW to TT bar is constant. And of course, it keeps the unitarity bound. Well, then you there. I hope it agrees, but in any case, you use the amplitude bound, but I used the optical there. Yeah? But in the simple situation, they should agree. One good thing about optical theorem is when we have two channels, TP bar with both helicity plus 1/2 and both helicity minus 1/2. The summation is inside of the right hand side. So this kind of factor, which you may need when you do amplitude analysis, kind of scale factor, is kind of automatic. So that's one thing, and then we need this TPH, which we study. But in addition, we have TPZ and TPW. And we all of them add, and when x equals pi, actually it goes like this. Okay? And so the interval bound is very low. Okay? Acutely, but then I realized this is not a unitarity bound of SMEFT, because we go back to the Lagrangian again. So let me see. So WW to TT is here, right? But there is also HH to TT has exactly the same coupling, right? But this HH to TT is also here, HH to TT. Right? So actually, the coupling of HHT is 3 times larger than pi plus pi minus pi pi t. And because of this, actually the HH to TTH, TT and HH to TTH cross-section is 9 times larger than WW to TT and WW to TTH. So the unitarity limit is reached much faster. And I studied this very carefully, and I realized that HH channel has the highest cross-section. That's why our last figure is HH. Yeah, this was really fun doing this. And I really worried. So focus equal pi, HH to TT bar is, this is just 9 times bigger than the WW to TTH. Yeah? But by summing everything up, the cross section is like this, and this unitary limit. Unitary limit is just left hand side should be smaller than 65, and this relationship can be expressed as in this case, WL is replaced by HL, okay? And then everything J equals 0 should be smaller than 65 over this. So we just draw the neutrality bound here, and we just give all the cross sections, and the total sum is here. And it's about 1.2 or 1.3, like 1.2. 1.3 is the neutrality bound. And as you said, new physics should enter major part of this. You know, the only example we know is the pi-pi scattering in Jericho 1. Yeah? The neutrality bound coming from this soft theory contact interactions is somewhere 1 point something, but unitarity is actually saturated at 770 at MED, right? At the low meson point. So it's much earlier. So I really do not know. Depending on the UV theory, this is in scalar channel, there should appear something. But that I don't know. All are speculations. So I just said that if it is pi, this assumes that the magnitude of the coupling is the same as the same, and then we study this. This is huge coupling, okay? 33 10 minus square. You never do it. It's a huge operation. And even with 0.1, it's still 5 7 minus square. So it's probably a typical days we can study maybe even smaller. Or if this is that if you take 0.1 and 0.35, it's kind of non-boundary physics is required. But in any case, the unitary bound is obtained like this, and that is the end of my talk. That's all.
Isn't that channel why the unitarity in the same way as the
Oh, yeah.
So it's the same.
Yeah, but the point is only HH channel has 3 times bigger coupling. So definitely HH channel. Yeah.
Is also safe. Using Goldstone point.
Sorry, let's check the Lagrangian. Okay. So which part are you talking about? Pi 0 square?
Yeah, so the pi 0 show.
Yeah, but the pi 0 square appears only here. So actually it is the same as W plus W minus. Okay. And for pi 0, pi 0 cube.
Yeah, so that's pi 0 cube.
Oh, okay. So for the three particles. So ZZ to TPZ is the same as HH to TPZ. That I agree.
Yeah.
But the two-body channel is small, so it cannot compete at the same time. It's only HH to TP. HH TP. Yeah. HH TP has 2 HH. Okay. But the pi 0 square does not enter here. Okay. Of course, the H pi 0, but it's only here.
Yeah, this one from inside.
So I think it will be 0.
So we don't discuss standard model yet. They're also perplexing with height. No standard model yet. They call it Higgs effect. Where they write down effective field theory, using only the singular case.
Yeah, but then you need to find the JV variant so to produce this effective fix, right? Otherwise, boson theorem, so
it does not violate.
We never know if that's a game theory or not.
Yeah.
And at least until some form of regular pixel is found, I cannot accept this complex equation. That is my view. You know, Higgs boson in the unitary case is a very strange object. I really don't understand how they can be real. But at least one concrete example I want to see together with people. Then maybe we can start thinking. But without this, actually, we cannot start thinking.
So there are some discussions. Trying to study this. Of course, we understand that quest of a low cutoff theory. The cutoff of the theory is 4 pi, roughly at 4 pi. And like Monahan said, oh, there's you can have a field dependent renormalization of the gauge field because geometric interpretation have. There's a field work. It's not beautiful. It's not a really complex thing. That's
does it have a growth function? It should have that.
Yeah, it has to.
So then both of those invariant theorem should be.
Yeah, what is
That
that?
both of those invariant theorem should be test numbers.
Yeah.
If the model is okay on it.
Yeah.
That's always the only way.
They have other operators.
Mm.
Blind operators. Essentially, they all higher power.
So I would think that just by checking if it is okay or not, can check by starting the boson because that's really exact. It's just a gauge invariance state. Any questions? No, I really enjoy this. As always, I enjoyed all of them.
In fact, the LC claimed they measured the top-Yukawa phase by doing the interference of this Higgs channel. And whenever you pose the question whether top-Yukawa's phase, what's the phase of that one? All the one phase actually means that.
Yeah, that's very important.
Yeah. But current LC circuits already start trying to use the sign of the tower.
That's
The phase.
Yeah. Very interesting.
So I say the top, I just keep my calculation in mind. So if you flip the top of your tower sign, the Higgs boson coupling will increase by 50%. We are having a CP violation to have a 3 years. It was really a conflict. Right. You not you get off for example, yeah, it depends. Yeah, but it becomes right? Yeah. I like to play this game, so I play this game. So if no more questions, I send Kaoru again and